Welcome to lecture 4 of AI 61003 Linear Algebra for AI and ML. The topic for discussion today is norms and distances. Norms and distance. So this important concept of norms and distances has a lot of important applications in AI and ML. We will see these applications when we discuss the examples of norm. So one of the most important norms that I'm very sure would have seen is this particular thing. So let x be a vector in Rn. Let x be a vector in Rn, and just to revise the notation, x is equal to x1 up to xn. It's an n vector. x1, x2, xn are components of this vector x. Then 2 norm of x, or sometimes I'll just denote it as this, is actually defined as square root of x1 square plus x2 square plus xn square. I just sum the squares. I just find the sum of squares of coordinates of this vector x and take the square root of that. That's 2 norm of x2. This is called as Euclidean norm, or 2 norm. So of x in Rn. So this is what this norm is called as, and you can see this norm is a very interesting thing. You can think of it as a generalization of absolute value for x in R, correct? And how do you see that? So suppose x is in R, then 2 norm of x is basically square root of x square, and I'll always take positive square root by definition, so it becomes absolute value. So this is how you can view 2 norm as generalization of absolute value. So with this understanding, the geometric meaning for n is equal to 2. What is the geometric meaning? So this is nothing but x1 square plus x2 square. And what does that mean? That means that if this is the vector x1, x2, this is 0, then the length of this vector x1, x2 is basically 2 norm, right? So this particular distance, length of x is 2 norm. That's how we will understand this. So this length of vector x, this formula we have already seen probably from 12th standard, the distance formula, usual distance formula that we speak of. And the 2 norm of a vector in general is the generalization of this concept of distance from origin. So so we will list down the properties. We'll list down the properties of 2 norm. Okay, so we'll prove all these properties. Let's just first write down. So the first property is non-negative homogeneity property. So what is non-negative homogeneity property? For every alpha in R and x in Rn is mod alpha norm xn. So in inner product spaces, in inner product or dot product, the way we defined it, we had this homogeneity property, but there the alpha came out straight away. The linear functionals, the alpha came out. Here what we need is the absolute value of alpha, because we are only looking at positive square roots. And then one of the important properties that we look at is triangle inequality. So what is triangle inequality? So for every x and y in Rn, x plus y, norm of x plus y is less than or equal to norm of x plus norm of y. So that's the triangle inequality. Then the third property that you have is non-negativity. So this non-negativity actually tells that for every x in Rn, norm of x is always greater than or equal to 0. And what is the last property? The last property is definiteness. And what is this definiteness saying? That norm of x is equal to 0 implies x has to be equal to 0. And the converse is obviously true. If x is equal to 0, then you are looking at 0 square plus 0 square plus 0 square under root of that, which is always going to be 0. So this actually is if and only if. But the more non-trivial one that we are looking at is this, that if the norm of a vector is 0, then the vector has to be equal to 0. So that's the definiteness property that we are looking at. So these are the 4 properties that this norm satisfies, out of which you can very easily verify that this property is true because we are always going to take positive square roots. So this property, the non-negativity property, is not a problem. Once you have this non-negativity property, non-negative homogeneity makes sense, and the definiteness is also fine. The important property that we want to look at, is a triangle inequality. So before going that, let's first think of why definiteness is important. So you consider this 2 norm of x is equal to 0, but by definition, so this is same as saying that 2 norm square is actually equal to 0, and this by definition is x1 square plus x2 square plus xn square is equal to 0. Now x1 square, x2 square, xn square, they are all non-negative numbers and they are all adding up to 0. So sum of non-negative numbers adding up to 0, each of that non-negative number has to be equal to 0. So this implies that xi square has to be equal to 0 for every I, which implies that xi has to be 0 for every I belonging to 1 to up to n. So that means that the vector x is actually equal to 0. So once again, to make sure that you understand what is really happening, this is scalar equality, and this scalar equality, which is true for all the n's 1 to up to n, means that this vector equality holds true. So this equality is vector equality. The 0 on the right hand side actually is a vector 0, and 0 on the right hand side of the previous step is actually the scalar 0. I am not making distinction here, but this is the definiteness, and the converse is obviously true. If x is equal to 0, then 2 norm of x2 has to be equal to 0. So this definiteness is fine. So triangle inequality is something that we really are interested in proving, and this triangle inequality is something that is really very interesting. Okay, so this triangle inequality that we want to prove is actually a consequence of Cauchy-Schwarz inequality. Okay, this is one of the most important inequalities in linear algebra, Cauchy-Schwarz inequality, and I am sure you must have encountered this inequality before also. So we will prove this Cauchy-Schwarz inequality today, and with the help of Cauchy-Schwarz inequality, we will show how triangle inequality holds true for the 2 norm. But before that, I want you to observe something. So what is it that we want to observe? Let's observe that for 2 vector x and y in Rn, how can you compute norm of x plus y? Okay, norm of x plus y. What is the formula? So basically, if you observe, norm of x by definition is x1 square plus x2 square plus so on so forth plus xn square, which is nothing but square root of x transpose x. Nothing but square root of x transpose x. Sometimes this I write as inner product of x with itself as well. Okay, so this is this is square root of x transpose x. So if you look at it, so I am only looking at 2 norm. So this 2 norm is basically x transpose x, right? So this is something that is important that you observe by definition, and then I can write down x plus y 2 norm square as x plus y transpose x plus y. That's how I can write down, and then I can expand this x transpose x plus x transpose y plus y transpose x plus y transpose y. This is simple rules of dot product or inner product that we saw in the last lecture. So this, if I can write down, is x transpose x plus 2 times x transpose y plus y transpose y, because x transpose y is same as y transpose x, it's just a scalar. So this is equal, and again this actually is equal to this plus 2 times x transpose y plus this, and this implies that 2 norm of this vector x plus y is basically square root of this x square plus 2 x transpose y plus y square. So this is something that is interesting to note, how this 2 norm actually is related to the inner product. In fact, 2 norm many a times is said it's induced because of the inner product. So first there is an inner product structure, you define the inner product between the two vectors, and you take inner product of a vector with itself, and that will give rise to the square of 2 norm. So that is something that is really very interesting to know. So this addition is something that is really very important. We will make use of this addition. So what I want to do is I want to prove something which is called as Cauchy-Schwarz inequality. Okay. So henceforth I will just write down CS inequality. So this Cauchy-Schwarz inequality is what we want to prove. And what does the inequality say? The inequality says that for every x and y belonging to Rn, absolute value of x transpose y is less than or equal to x norm of x times norm of y. So absolute value of x transpose y is less than or equal to norm of x times norm of y. This is true for any n vectors. If you want, sometimes it is also written as x1 square plus xn square square root y1 square plus yn square, right? That's the formula. Many times if it is introduced before linear algebra, people try to write it in this second form, but in the linear algebra notation, this is what we will write down. So what am I going to do? I am really going to prove this inequality, and the way we are going to prove this inequality is the following. So the first observation is that if x is equal to 0 or y is equal to 0, then equality holds and we are through. And we are through, right? There is nothing to prove because both the sides are 0 and there is nothing to prove for us. So what we do, we start with an interesting vector. So what is the interesting vector? Let alpha to be norm of x and beta to be norm of y. So alpha and beta are two scalars. Because I am taking x and y both not equal to 0, they are both non-zero scalars, right? And what vector I am considering? The vector that I am considering, consider the vector alpha y minus beta x. I'll consider the vector alpha y minus beta x, and then because this is a vector in Rn, clearly this is a vector in Rn, what I really know is that alpha y minus beta x 2 norm square is greater than or equal to 0, right? This is true for 2 norm. We already have proved that this is nothing but sum of squares, so it has to be greater than or equal to 0. So this property holds true. And what do we know of this particular thing? So this particular thing basically is same as alpha y minus beta x transpose alpha y minus beta x. That's the definition of 2 norm. And if you simplify this further, what would you get? If you simplify this further, you will get that. So if you can allow me, I will just write down alpha square y transpose y minus alpha beta y transpose x minus beta alpha x transpose y plus beta square x transpose x. That's the term that I am going to get. And if I rearrange these terms properly, what is it that I am getting? So 0 less than or equal to, I will get the first term alpha square norm of y square plus beta square norm of x square minus 2 alpha beta into x transpose y into x transpose y. That's what I am going to get. And now you remember what are these alpha and beta basically are. These alpha and beta are nothing but 2 norms of x and 2 norms of y respectively. So they are positive numbers, so I divide by those positive numbers. So I divide by product alpha beta, I will not change inequality, and when I divide by that, what am I really left with? So first write down this alpha square. So what is this alpha square? Alpha square is norm of x square. So you have norm of x square norm of y square plus norm of y square norm of x square minus 2 norm of x norm of y x transpose y, and you are saying that 0 is greater than or equal to this, and I will divide by norm of x norm of y. So if I divide by this, what am I left with? What am I really left with is the following. I divide by 2 as well. So this will tell, I will transfer this x transpose y on the left hand side. So this will tell that x transpose y is less than or equal to norm of x norm of y. I hope you all understand what we have just achieved. And if we replace x by minus x, so x is a vector, similarly minus x is also a vector. So I do the entire business for x by minus x. So instead of this x here, I will put a minus x. So I am basically looking at alpha x plus beta, alpha y plus beta x whole square. Perform the whole analysis once again. What will I really get? I will really get minus x transpose y is less than or equal to this. And when I have this particular thing, this equation star and equation double star together will imply that absolute value of x transpose y is less than or equal to 2 norm of x times 2 norm of y, which is what Cauchy-Schwarz inequality is really. So that's the proof of Cauchy-Schwarz inequality. And one more interesting thing that you can observe here is that not only in the case when x is equal to 0 or y equal to 0 we are getting equality. In fact, you look at this particular equation. This particular equation, the inequality comes because of this vector which is actually non-zero vector. The strict inequality come here if alpha y is not equal to beta x. If alpha y is equal to beta x, then you will get a 0 vector inside this norm, and then there will be an equality here, and the equality will hold true. The x transpose y here, everywhere you will see there will be an equality. So the equality will hold true not only in the case when either x is equal to 0 or y equal to 0, but also in the case, so note, the equality holds true. Equality holds true when in our notation alpha y is equal to beta x, which really means that y is equal to beta by alpha x if alpha is not equal to 0. Okay, if alpha is not equal to 0. So what we really are saying is that one vector y is a linear multiple of another vector x. So if the x and y vectors are such that one is the linear multiple of the other vector, then actually equality holds in Cauchy-Schwarz inequality. So that is something that is really very useful, interesting, and this I think we will be able to see, we will be able to revisit this inequality once again probably when we are talking of correlation coefficient. So if we look at correlation coefficient, so what we have written here, the proof, what we have done basically is the proof of saying that correlation coefficient always lies between -1 to 1. So if you properly choose all these x and y and everything together, then what we actually have proven is that if you have two random variables x and y and you look at the correlation coefficient between them, then the correlation coefficient always lies between -1 to 1. That's what we have shown. And in fact, this is very much related to the concept that we will explore little further either today or in tomorrow's lecture of angles between the vectors. Okay, so when we define angles between the vectors, all of us remember that cos theta is always between -1 to 1 and so on and so forth. All these things are very much related to each other. Okay, and in this context of norm, why did we come to Cauchy-Schwarz inequality? We came to Cauchy-Schwarz inequality because we wanted to prove triangle inequality. So how does Cauchy-Schwarz inequality helps us to prove triangle inequality? Okay, so proof of triangle inequality. So if you look at x plus y whole square, then we already had written the expression x square plus 2x transpose y plus y square, norm of y square. That's how you can write down x plus y whole square. And now because of triangle inequality, what can you write down? Plus 2 times norm of x, norm of y plus y square, right? So from here to here I am using Cauchy-Schwarz inequality, right? So this is Cauchy-Schwarz inequality. So this equal to is changing to less than equal to, and because of this now it's just algebraic manipulation. You can observe that the right hand side here is basically this, so which will imply that norm of x plus y, its 2 norm is less than equal to norm of x plus norm of y, which is triangle inequality, which we have proven. And in order to prove that, we require Cauchy-Schwarz inequality. So the triangle inequality is being proved. So these are all properties. These are all properties that are satisfied by 2 norm. So these are the observations that we made. So where did we start? We started with this particular definition of norm or 2 norm, and we observed that this 2 norm satisfies all these 4 properties, and we in fact proved that every property is satisfied by this 2 norm. So what really happens is that these 4 properties are really very special, and they are a very important building block for defining a much important and much broader concept in linear algebra, that is a norm of any vector. Okay, so there can be many functions which will satisfy these 4 properties. So any function which satisfies these 4 properties will be called as a norm on Rn. So let's write down the general definition for norms. Any function f, so any function I will denote it like this, going from Rn to R, any function going from Rn to R which satisfies these four properties. What are those four properties? Non-negative homogeneity, triangle inequality, then the third property is non-negativity, and the fourth property is definiteness. So if you can find out any function from Rn to R which satisfies all these properties, then that function is called as norm. Then is called as norm. And what are the examples? One example is 2 norm from Rn to R. We actually proved that this function is norm. So that's the formula. That's what this function does. X is being sent to, the vector x is being sent to this number. The second example is P from Rn to R. We call this P norm. And how do you define this P norm? The way we define this P norm is the following. So this is basically mod x1 to the power p, mod x2 to the power p, plus mod xn to the power p, the whole thing to the power 1 by p. That's the formula for p norm, and p equal to 2, you get the norm that we were discussing so far in this class. So that's why I'm putting a sub 2 now. So this sub 2 that I put here is a special case of this p norm. So this is a norm. So this is a norm for p greater equal 1. So for any p greater equal 1, this particular function becomes a norm. So one interesting norm that you can look at is p is equal to 1. So when p is equal to 1, you are just adding the absolute sum of all the coordinates. So one norm of x is mod x1 plus mod x2 plus mod xn. So that particular norm is also a very useful norm in many applications. Absolute sum norm. Okay, so p is equal to 1, absolute sum. P is equal to 2, Euclidean norm. Many a times it's called a spectral norm also. So P is equal to 2, spectral norm. The relation of P is equal to 2 is when you consider signals as vectors, like audio signal or signals in control theory. The interpretation that you can give to this P is equal to 2 spectral norm is that of energy of a signal. So that is something that is very useful interpretation. Many a times people want to talk in terms of energy of the signal, and that can be done through P is equal to 2 norm. Another interesting norm is infinity norm. Infinity norm, sometimes called as sup norm. In our case, it will be maximum norm. So what is it? It's defined as maximum value of mod xi I equal to 1 to up to n. So you choose the absolute maximum value in this particular vector. That's the norm. So you can actually show. So all these examples that I am discussing, you can actually show that all these 4 properties hold true. Almost always you will realize that property 1, non-negative homogeneity, property 3, non-negativity, and property 4, definiteness hold true and you can prove very easily. The challenging part is triangle inequality. So in this particular p norm case, or in this particular infinity norm case also, not so difficult, but it's challenging to prove the triangle inequality. So I invite you to try and see if you can prove triangle inequality for these particular vectors. These norms, why are they important really? Because they actually help us quantify the vectors with respect to their size. So this is something that is really very interesting. So if I say a vector x is there with a very small norm, then I will call vector x small. On the other hand, if the vector x is with a very large norm, then I will call vector y vector x large. So this small norm or small vector, large norm or large vector, they are subjective terms, but those subjective terms are something that, so what to call small, what to call large will actually depend on the application that we are working with. So we will see plenty of such applications little later, but you can actually use norm to quantify the size of the vector, so to speak. So far there was no means for us to quantify the size of the vectors. If you wanted to compare the vectors, now this is one way in which you can compare the vectors. Okay, so this is not the only way. There can be more than this way to compare vectors, but this is definitely an important way, and now we can quantify which vector is small, which vector is large. So that's like getting ready, warming up for applications. Okay, so one important quantity that you can define is root mean square. Okay, root mean square value. And how do you define that? So root mean square value, so many of you might have encountered this RMS value. So what is this RMS value? So RMS value of x is actually defined as x1 square plus xn square divided by n. So what is this? This is basically the average of the square of the norm. So this is what this thing is. So you look at average of the square of the norm and take the square root, that's root mean square. So what is mean square? So the entity here is actually called as mean square of x. Mean square of x, and this is a very important entity because this will help us compare vectors of different sizes. Okay, so we will come to that little later when we look at RMS error, but you observe this fact here, which is a very useful fact. So what is RMS of x really telling us? RMS of x is really telling us what is roughly on an average value of mod x. So average value is not a good way of saying typical value or typical value of mod of x. That's what this root mean square error is basically telling us. And one thing that you note here is consider this vector 1n. So what is the RMS value of 1n? The RMS value of 1n is 1 plus 1 plus 1 n times divided by n, which is equal to n for every n. So you take this one vector in any space, n dimensional space, the RMS value will always be equal to 1. But if you look at the 2 norm of 1n, then this 2 norm of 1n is basically square root of n. So as n changes, the value of 2 norm changes. So you take n is equal to 100, then 2 norm of 1n is actually 10, square root of 100. But RMS value of 1n for any n is always equal to 1. So this actually is the observation which will help you understand the concept that you can use the RMS value of a vector to compare the two vectors of different sizes. So for some reason you look at 1n, so you look at these two vectors 110 and 100. Now which of these two vectors is small or large? This is really vague, so you should not take it in exact sense of small or large. But 110 and 100, if you look at these two vectors, then the 2 norm is basically square root of 10 here, and 2 norm is square root of 100 here, which is equal to 10. But both these vectors will have 1 as its RMS value. One vector is length 10, another vector is length 100, and the RMS value is still same. So I would need to compare this 110 and 100, and I would like to see which one is better. Why I would like to do that, we'll come to that little later. Towards the end of this class, we are going to look at it, and then you will realize that why I am making so much of fuss about comparing two vectors of different lengths. That's something that we'll look at. So another interesting inequality that you encounter is Chebysev inequality. Those who have done probability statistics class, they will realize that they have already seen this Chebysev inequality in a different form. So we will try to relate what we are doing right now with that form also. So what is this Chebysev inequality really? So let x be a n vector. So let x belonging to Rn, and let there be k entries in X such that mod xi is greater than A. A is a positive scalar. Mod xi is greater than A, where A is greater than 0. So you find out some real number A, and what are you saying? That there are k entries in the vector such that the absolute value of those k entries is bigger or equal than this constant number A. If that is true, then obviously xi square is bigger or equal to A square, and if that happens, then norm of x square, which by definition is x1 square plus x2 square plus xn square, is clearly greater than or equal to k times A square, because at least k of the entries are bigger than or equal to A square because of the assumptions that we have made, and the remaining entries are non-negative entries. They can be 0 or they can be anything, but they are non-negative, so this inequality will be satisfied. So if this inequality satisfies, then what is it that we are really saying? So we are really saying that this norm is greater than or equal to k A square. And then you will ask me, what is big deal about it? The big deal about it is that if you can look at it in terms of RMS value. Okay, so in terms of RMS value, how can you write down Chebysev inequality? You can write down this Chebysev inequality by k by n is less than or equal to RMS of x divided by A whole square. So this is something interesting. So what did I do? What is the relationship between norm of x square and RMS? So both the sides of this inequality. So I have this inequality which we are calling Chebysev inequality. Both the sides of this inequality are divided by n. So this side is actually RMS square, and this side is Ka square divided by n. So I take this a square on this side also, so that's what I am getting. RMS of x divided by A whole square is greater than or equal to k by n. So this is something that is really very interesting, and what is the meaning of this, we will look little later. Okay, so this is the Chebysev inequality, and what do you make out of this Chebysev inequality? How do we interpret this? We will come to it in a short while. Okay, so this is about norms of vectors. Okay, so given a vector, I have defined norm. So with help of norm, now I am going to define something which is called as distance between the two vectors. Right now what am I really doing? I am really defining norm of a given vector x, and what does that norm of the given vector x tell me? It tells me what is the length of that vector, or what is the distance of that vector from the 0 vector. That's what the norm is really telling me. But now if I am given two vectors x and y in the plane, or x and y in arbitrary space Rn, I want to find out distance between these two vectors. And how can I find the distance between the two vectors? With the help of norm. That's what I am going to do. So the next thing that we want to look at is distance between the vectors. So Euclidean distance. How is it defined? It is defined in terms of norm. So for x and y belonging to Rn, distance between x and y is actually defined in this particular way. Distance between x and y is actually defined in this particular way. So what are the properties? The properties of distance is always greater than or equal to 0. Distance will have that homogeneity property, and the third property is that triangle inequality. So what is the triangle inequality saying in terms of distances? So in terms of distances, this is the triangle inequality. What does it say? Distance between two vectors x and y is norm of x minus y. Distance between two vectors y and z is basically norm of y minus z, and distance between x and z is basically norm of x minus z, right? That's what you have. So what is triangle inequality really saying? So suppose this vector is x, this vector is y, and this vector is the z vector that we are looking at. Then you look at this. So the norm of this x minus y I am writing here in this particular way. So that's the distance. This is the distance y minus z, and this is the distance or the length x minus z. And what we really know is that if you directly travel from x to z along the straight line, then that distance is always less than or equal to the distance that you will travel to go from x to y in a straight line and y to z in a straight line. That's the triangle inequality. So what is it saying? It's saying that distance between x and z is less than or equal to distance between x and y plus distance between y and z. So that's what triangle inequality is saying. And what is this? So this is actually x minus z. And what is this x minus z? So this x minus z, I can write this down as x minus y plus y minus z. So this is nothing but, so these are all two norms. Okay, so now henceforth please remember that I will always consider two norms of the vectors unless otherwise specified. So if I don't write down the subscript 2 here, by default it means that I am talking of two norms. So if I forget that subscript, you please remember that it's two norm that I am speaking of. So x minus y is one vector, y minus z is another vector. Then using triangle inequality, what do I know? X minus y plus y minus z. So that's triangle inequality of the norms, and that leads to triangle inequality between the distances. But this geometric intuition of the distances is really very clear. So that's the distance or Euclidean distance between the two vectors. That's what we are looking at. And now let's look at the examples of the distance between the vectors. Okay, so the first example that we want to look at is that of feature distance. Feature distance. So if x and y represent, so x and y in Rn represent features. So these represent features of two objects. Then what we are really going to look at? We are going to look at norm of x minus y. And what is this norm of x minus y is going to tell us? If this distance between x and y is small, distance between x and y is small, then you will like to say that x and y are similar, they are close to each other. So as far as the features are concerned, these two objects are similar to each other with respect to the features that you have drawn. So for example, you can consider a very interesting scenario that is close to your hearts. So for example, x and y is a feature vector corresponding to two students in a class. Those two students have registered for this particular course, AI 61003 AI and ML, linear algebra for AI and ML. And what are the features corresponding to these two students? So the first feature, so the first component of x is the number of hours of self study that you put in that you put in for the course. The second feature is number of classes that you attended. The third feature maybe is the performance in the mid semester examination, and so on and so forth. So there can be n features in this particular way for x, and similarly the same values will be there for vector y, the feature of student 2. And now if you look at the difference between the Euclidean norm x and y, and if that distance is very small, then what you would expect is that the grades that you will get in this course are same or similar, right? That's the similarity that you are really looking at. But if the distance between these two vectors x and y is really far apart, then what you will really like to do is that you will say that the student corresponding to x and student corresponding to y are not so similar and they should get different grades. So that is something that is really very important. So that's how this feature distance is going to play a role on certain decisions that you are going to make. So this feature distance is something that is important. But again, once again, please remember that what is the difference between the distance, okay, what is the distance that you will call small and what is the distance that you will call large depends on the application. So for example, the distance between x and y you may think is small, and hence you should get the same grade as your friend who performed more or less same in your thinking. But as far as I am concerned, that distance might still be large for me, and I will say that no, your performance is not same as far as I am concerned, because I am calling certain distance small and you are calling the same distance large, or vice versa, right? So it is personal, it is not objective. So this will change from application to application, what you will call small and what you will call large. But at least there is a quantification now available with respect to you. So there is some number available with respect to you. Whether to call that number small or large will depend on the application that you are really considering. So that is something that is important. So that's how you will use feature distances. Okay. The next thing that you will like to do is RMS prediction error. RMS prediction error. So what is this RMS prediction error really? So let y belonging to Rn is a time series, for example. Okay. So there are certain values y1, y2 up to yn present in this vector. Those y1, y2, yn values actually represent the values of the time series at time instant t1, time instant t2 up to time instant tn. And by some means, by some model that I have already built, I can predict these values of the time series. So the predicted values, so these are the values. So y observed time series, okay, observed time series, and yi's are actually the observed time series values. And similarly, y hat in n, another vector, is actually predicted time series. Okay, so this predicted time series might come out because of the model that I have built. So this y minus y hat is prediction error. So y minus y hat is prediction error, and the 2 norm of this y minus y hat is the prediction error norm. And if I look at the RMS value of y minus y hat, then I am sort of normalizing it. I am dividing it by root n. By root n is actually the RMS value of y minus y hat, right? That's what I am looking at. And based on whether this value is large or small compared to the RMS value of y, I can decide whether I have built the model which is reasonably good in prediction or not. So this is something that is really very important. But now consider the scenario that I was talking of, why the RMS value is really very important. In order to just check whether the model is good or not, I can just stop at norm of y minus y hat, the prediction error norm, and if that is small, I will be happily accepting. But this RMS value is really very important, because if I have more than one model, so model 1 predicts values at n1 time instances. That's how the model is built. It can predict only at n1 instances. N2 can predict only at n2 instances. The sizes of the vectors are different, but now you still want to say which model is better. Now if you just look at the norm, then the norm will depend on the length of the vector. So sometimes norm will be large, sometimes the norm will be small. So the case where you have large norm, because of the size of the vector, you will be sort of concluding probably in a wrong way that that model is not good. Whereas if you look at the RMS value, what is RMS value telling? RMS value is really telling what is the typical value that the ith component of absolute value of y minus y hat takes, right? So that's the typical value with which you really want to compare the performance of the model, not the norm of the vector. So that is why RMS value really comes into the picture, and this is the scenario where you might be required to compare two vectors of different sizes, and when you compare the two vectors of different sizes, RMS value actually helps you to do that rather than norm. But RMS value of course comes from norm. And once again, what RMS value is good, what RMS value is bad, to decide that the model is good or bad, that's subjective. That will depend on application. So your application will dictate what you want to say, a good thing or a bad thing. The next example that I want to look at is that of nearest neighbor. Okay, so let z1, z2 up to zk be k vectors in Rn. Okay, and let there be another fixed vector x in Rn. Then we say ZL is the nearest neighbor of x if ZL minus x is less than or equal to Zi minus x for I is equal to 1 to up to k, right? So out of these k vectors z1, z2, zk, you want to find out the nearest neighbor to x. So what is the vector which is nearest to x? That's what you want to find out, and it's pretty straightforward. This particular vector zl will be called as nearest neighbor of x if absolute value of the norm of zl minus x is less than norm of all. So zl is closest to x in terms of the Euclidean distance that we have defined, right? And in the same tune, you can define nearest m nearest neighbors. So you can take m is equal to 2, so 2 nearest neighbors. So similar way you can define this, and so on so forth. So this so m nearest neighbors or the nearest neighbor play a very crucial role, important role in one of the many important algorithms, k-means clustering. So that is something that you will see in subsequent classes or in your assignments. So this concept will come very handy. This is something that is really very important. So this is what I want you to look at. And before we close today's lecture, I think I should say one more thing. Units for vector entries. Okay. So that is something that is very important. So for example, consider the scenario. Consider the scenario of vector x1, x2 up to xn. Okay, so these vector x1, x2, xn are actually feature vectors, and those feature vectors have only two features. So x1 has two components, x2 has two components, and so on and so forth. So the vector x1 has two components, vector. Okay, so for the sake of easy discussion, I will take x, y and z. So I can use x1, x2, x3 as components if I want to, maybe. So this is my x, this is my y, and this is my vector z. Okay, and the entries, the first component are in thousands, and the entries of the second component are only in units. Okay, so typically x can be of the type 1502, y will be 1603, and z will be 1605. Okay, so I will make this 2 to drive the point home. Okay, so if you look at vectors x and y, their second component is same, their first component is different. And if you look at vectors y and z, their first component is same, but the second component is different. Okay, so the distance between x and y, the Euclidean distance between x and y is actually 10, right? You have 1500 minus 1600, that's 100, and 0, the norm of vector 100, 0 is 100 square, so the distance between them is 100. Whereas if you look at the distance between y and z, that distance is 3. So if you just look at the distance as is, then you will say that vectors x and y are very dissimilar, but vectors y and z are very similar to each other. But probably that may not be the case, because the first entry that you have in vector x, which is 1500, 1600, 1600, those entries are in thousands, and a difference of 100 really does not make much difference. The difference of 100 in the first entry is same as difference of unit in the second entry. So if you understand what I am really saying, then just looking at the norm is also sometimes may not be really enough. You want to scale the entries in the vector before you calculate the norm. So instead of looking at these entries as 1500, 1600, 1600, if I look at them as 1.5, 1.6, 1.6, and then I look at the norm, then 1.6 and 2, 1.6 and 2, 1.6 and 5, the entries, both the entries in the vector are sort of on the same scale. And now if I look at the Euclidean distance of the scaled vectors, so to speak, then probably I will get much more meaningful similarity distinction between the vectors x, y, z now, rather than just looking at x, y, z as I have them here. So this type of scaling that I really want to do is a very crucial point. This point is really very important when you want to compare vectors, and the vectors are such that the entries in the vectors are in heterogeneous units. Okay, so that is something that is really very important. So if you just blindly take the norm in this particular case and hope for the best results of whatever AI ML algorithm that you are using, probably you will not get those results. But if you do the scaling to these vectors and then do something with the norms, the differences, the feature differences, and so on and so forth, the chances are higher that you will get the desired results. The chances are higher that you will get the results that you really want to see the algorithm giving to you. But then it is not fault of the algorithm, it is fault of how you define similarity. So there needs to be some scaling done here. So this gives rise to one of the most important concepts in the norms, that we will talk of weighted norms. So we will not just take norm of x as x1 square plus x2 square plus xn square. Maybe x1 square I want to scale appropriately with some number. So in this particular case, x1 square I want to divide by 1000. So the norm that I will consider is x1 square divided by 1000 plus x2 square. So if I define the new norm in this particular way, will it be a norm in first place? Will it satisfy all the properties that I listed there or not? So that is something that is really very important, the concept of weighted norm, and we'll focus more onto this concept of weighted norm in our Friday's tutorial. But this is very important point as far as applications are concerned. So please remember that only norm sometimes may not be enough, and you want to take the weighted norm in order to take the point. Okay, so that is something that is really very important, and please remember this point. This will play a very key role, crucial role in the applications that you are handling. So to summarize what we have done today, we defined the norms of norms on Rn. So the norms were like P norm, in particular 1 norm, 2 norm, infinity norm. We listed 4 properties that these norms actually satisfy. So they are actually the defining properties. So these defining properties, one of the important defining properties is triangle inequality, and in this triangle inequality we used Cauchy-Schwarz inequality to prove it in case of 2 norm. For other norms we have not proved the triangle inequality, but you can prove it with some difficulty. And once the concept of norms was defined, we defined RMS value of a vector x. We talked of Chebysev inequality, and based on norms we defined distance, and the concept of distance we saw some examples, and weighted norm or weighted distance, weighted norm or weighted distance, which will play a crucial role in applications. So this is what we studied in this particular lecture. Thank you very much.